differentiation, and this problem, as you can see, it isn't in terms of any variable. Both of them are on the same side, so you could solve for y and find the derivative normally, but that takes more time, and implicit is a lot easier. In this, you will derive in terms of x, so when you take the derivative of the x value, it will go to dx over dx, so that just cancels out. But when you take the derivative of the y value, it goes to dy over dx, so that will be a normal derivative. Just because I forgot to explain this part, so when you take the derivative of something, you pretty much multiply the d over dx to it if you're doing it in terms of x. So what d is multiplied on the top is what the function you are taking the derivative of is. So when you are taking the derivative of the x in the implicit, this would be x, but because they're the same variable, and it's the same on the top and the bottom, that equals 1, so you can pretty much not include that. But when it is of y, it would be dy dx, and you can't cancel that out because it's the derivative of the y value in terms of x. So in this problem, you want to take the derivative kind of normally, except you factor in the dy dx's throughout. So this, it would be 2x, and we could write dx over dx, but that would just equals 1, so we don't need to do that. So it would add 2y, but then you have to tack on dy dx because it's kind of like chain rule, and that would just equal 0. So now we want to separate the dx over dx and the dy over dx. So you would subtract this from both sides. So now you have 2y dy d over dx equals negative 2x. And now you want to get dy dx alone, so it's the derivative. So you would just divide 2y from both sides, and so that equals the derivative, where it is dy over dx equals negative x over y if we simplify it. And that's an easy example of implicit, and we'll move on to the next one, which is a little bit harder, because in this one we're gonna have to use product rule. So we will derive this the same way we did the last one, but using product rule for this. So product rule is a times the derivative of b plus b times the derivative of a. So this would be x squared times the derivative of y, which is 1, but times dy dx, and then b plus b, which is y, times the derivative of a, which is x squared. So that would be 2x. And then the next one, the derivative of 2y is 2 dy dx, and the derivative of x cubed is 3 times x squared, and then 17 goes to 0. So now we will want to have all the dy dx's together and all the dx dx's together. So we can first put them near each other in this, so it would be x squared plus 2 dy dx plus 2xy plus 3x squared equals 0. And now we're gonna subtract 2xy and 3x squared from both sides to have them on different sides again. So that equals x squared plus 2 dy dx equals negative 2xy minus 3x squared. And then we're going to divide x squared plus 2 from both sides. And that will equal dy dx equals negative 2xy plus 3x squared over x squared plus 2. So we just took out the negative sign and would distribute it through it. This just makes it easier to look at, I think. So those are 2 examples, and we're going to move on to a third one, which will be a little bit harder. Okay, now we're on to our third example, and this one is called logarithmic differentiation, but you use implicit in it. So this is an example of a problem where you could use product rule, but it would be very long, and it's much easier to do logarithmic differentiation. So in logarithmic differentiation, you will take the natural log of the entire equation on both sides so that you can simplify things using the log properties. So we will write this out, and then through this will stay ln of y, and I'll just leave that out for now. But since in logs and natural logs you can bring down like the exponent and things, we're gonna use that to make this easier. So this will be 1/2 ln of x, and then this e to the x squared. Also, we can split this up because when it's multiplied in a natural log, they will be added together. So this will be plus x squared ln of e, and then plus 10 ln of x squared plus 1. And so we can simplify that down even more to 1/2 ln x plus 1/2, because ln of e actually just equals 1 because the base of ln is e. And then this will be plus 10 ln of x squared plus 1. And then we'll put in ln of y right here. So now is the time that we use implicit to solve this. So on this side, it will be 1 over y times dy dx. So that's easy. And then on this side, it will be 1/2 times 1 over x, and then we don't have to use the dx over dx because that just equals 1. And then the derivative of x squared is 2x. And then the derivative of this part is 10 times 1 over x squared plus 1 times 2x, because it's the chain rule, so you have to use the x squared, and that's the derivative of that is 2x. So now we have 1 over y dy dx. We're just going to simplify this down. Equals 1 over 2x plus 2x plus 20x over x squared plus 1. So now to get dy dx alone, we're going to multiply y on both sides. But when you do this, since we can't have y over here since we're just solving for x, we're gonna plug in what y equals up here for y. So it will equal dy dx equals 1 over 2x plus 2x plus 20x over x squared plus 1, which is the same, and then it's multiplied by root x times e to the x squared times x squared plus 1 to the 10th. And that part is our y value, but we just substituted it. So that is the end of my video about implicit differentiation and logarithmic differentiation. I hope it helps, and thank you for watching.